Hi everyone. In this video we'll study about collapse load. Okay. As per the last video we discussed related to simply supported members subjected to point load and simply supported both ends are fixed which is subjected to point load in the middle. So in this video I am ready to explain for proper cantilever members. So the question: determine the value of collapse load for the proper cantilever beam concentrated to or concentrated point load, right? So this is the proper cantilever member. Okay, proper cantilever in the sense, so one end is fixed, further end is simply supported. Okay, so this fixed end is naming it as A, and further end is name it as B. Okay, this AB member subjected to point load of magnitude W. Okay, this point is naming it as C. Okay, so then the distance between A to C is A, and the considered distance between C to B is B. So this is the given problem. We have to identify the collapse load for this particular problem, okay, by using static method or kinematic method. In the first step I am going to consider static method. Okay, in the next later we'll get consider the uh, kinematic method. Okay, so by using kinematic method, sorry, the static method. Static method in the sense, so we know that so that is the total maximum bending moment at any point, which is equals to total plastic moment at any at that point. So in this, before going to the previous problems we are considered that, so in this we are also same consideration. Before going to that, I am going to draw the bending moment diagram for this particular condition. So the due to the point load, the bending moment is developed like this. Okay, so this is a 1. So another, due to the fixity, so we are having a bending moment diagram like this. So these values this value is called it as a MP. Okay, so this one is a MP, and this is also MP. Why it is MP? So why it is called it as MP? So we know that locations of plastic hinges, so based on the that all those 8 points, so out of 8 or out of that points, so due to the fixity we are going to identify the plastic hinges or plastic hinges developed at the fixity, and also plastic hinges is developed at under the point load, right? So that's why, so we are going to consider bending due to the from this bending moment diagram we are getting. So since the static bending moment at C is greater than at A, okay, from this figure, so the plastic moment at C is greater than A. So the plastic hinge will first develop at C and later at A. Okay, the structure will then converted into mechanism, and it will ultimately collapse. Okay. During collapse, the moments at both A and C will be MP. Okay, the moment both at points A and C, it will be MP. So due to this point load, we are getting that maximum bending moment value, that is WC into AB divided by L. Okay, and so we are having the maximum bending moment value. So that is the maximum bending moment, that is WC into AB divided by L. Okay, so then another equation, so that is the bending moment at that point or plastic moment at that point, so that is one is MP. Okay, from this MP we are going to consider, so one more MP at from the fixity, so that value is MP into B by L. This study is taken from the deflection of beams, and in so many cases we studied, so that is MP into B by L. Okay, so from this so we are going to take MP is taking common out of these two, so the equation is like this: B by L, remaining thing in this B by L. So then again I am going to take LCM on this, MP into L plus B divided by L. Okay, right, L plus B divided by L. So this is WC into AB divided by L. Okay, by simplifying, so WC, which is equals to, okay, WC, so this WC, which is equals to L divided by AB into MP into L plus B divided by L. So this L get cancelled. Okay, so then L plus B into MP divided by AB is our collapse load. MP into L plus B divided by AB is our collapse load for propped cantilever members subjected to point load in a varying distances. Okay, so right, so the question is like this. So to identify or to find out the expression for collapse load for propped cantilever member subjected to point load at a distance of A from the left support. Okay, so like this. So then in by using a static method, we are getting the collapse load, and then I am going to then go to the next method, that is a kinematic method. By using kinematic method, by using kinematic method, so in this kinematic method we have to draw the, that is mechanism, that diagram. So that is a mechanism diagram. So this is a diagram like this. So here theta value is varying because of point load is varying distances. So that's why this is deflection. Okay, and this one is the theta and this one is theta 1. I am going to consider this distance is A and this distance is B. Okay, so right, so this is the A and this one is sorry, at A we are having theta, at B we are having theta 1, that is these are the rotations. So due to this, so opposite angles are equal, so this is a theta 1, this is a theta, and based on location of hinge points, so due to fixity we are going to consider 1 MP at the A. Okay, and B and is simply supported, there is no plastic hinges developed. Okay, then also similarly we are going to consider at the point, under the point load, so that is MP and this is also MP. Okay, so the condition is or the work done, okay, virtual of work done. So external work done, which is equals to internal work done. External work done in the sense the load into displacement. Okay, and also internal work done in the sense what, moment into rotation, or so like this, load into displacement. The stiffness in the sense so load is required to produce unit displacement. Okay, similarly the moment is required to produce unit rotation. Moment is required to produce unit rotation. The both are equations, or both are external and internal work done. So so we are going to equating these two. So what is the load for particular problems? Okay, this is a collapse mechanism for beam. Okay, so then external work done. Okay, so we have to identify delta value for identification of load into displacement. This is load application is WC, and due to this application of load, the displacement is developed at delta. So you have to consider the triangle. Okay, this is the theta value, this is the delta value, this one is the distance A. Okay, so this end is A, so we are going to consider this triangle, okay, for identification of delta. So I am going to apply the tan theta over here. So tan theta in the sense opposite by adjacent, adjacent is A. Okay, so the theta is very small, so that's why tan theta is into theta. Okay, so delta divided by A, we need the value of delta, so delta, which is equals to theta into A, or A theta. Delta is A theta. Okay, so displacement value is A theta and load is WC, so load is WC into theta into or a theta. So this is our left hand side, that is the external work done. Okay, for internal work done, so moment into rotation. So how many rotations are there in this particular problem? We are having two rotations, one is a theta, another one is a theta 1. Theta is developed at the a point and theta 1 is developed at the b point. Okay, so theta in the sense we know that delta by a, or we can identify theta 1 in the sense what. So similarly we are going to consider another triangle. So this triangle I am going to consider. So this is the theta 1, this is a b, this is the delta value a theta, we already identified. Okay, so that's why, so tan theta 1 or theta 1, which is equals to opposite is a theta divided by adjacent side is b. So theta 1 is equals to a theta by b. Okay, this is the value. So due to the locations of points also, this is a mp theta 1 is a 1 value, so another one is mp theta plus mp theta, so one more mp is there, that is mp theta. Okay, this is the moment and this is a rotation. Okay, the both are in same direction, that is a positive sign. So the rotation and plastic moment is in the opposite direction, we are considered it as a negative sign. Okay, so both are in the same direction, so that's why we are going to consider positive. So mp theta 1 plus mp theta plus mp theta. So right, so now the 1 mp theta, or sorry mp theta 1, so into a into theta divided by b plus 2 mp theta. Okay, 2 mp theta. So this is wc a into theta. So wc a theta is the left hand side. So in the right hand side, so I am going to take mp is a common term. Okay, and also we can take theta value also, so mp theta. So remaining terms is a theta by b plus 2 is our value. Okay, so here theta theta get cancelled. Okay, so wc into a or mp by a into a theta by b plus 2, a theta by b plus 2. So by simplifying so or taking the LCM on this end. Okay, so right, I am going to go to the next in this side. So mp into, okay, 2b, okay, by taking the LCM, 2b plus a theta divided by b, so whole divided by a, right? So this is the right hand side equation I am going to write, right, only writing this. So mp into, okay, 2b plus a theta, 2b plus a theta divided by ab. Okay, so now theta is already taken common, no, right, in this, right, this theta is not coming, right. So a by b only will count taken out in the remaining thing. So a plus 2b, a plus 2b divided by ab. Okay, so then after simplifying this we'll get mp. Okay, so l in the sense what, and l plus b we required. Okay, so you have b is that one thing, so 1 a plus b is our l, right. So like that l plus b, after simplifying this we are getting the solution mp into l plus b divided by ab is our solution. So this is a collapse load wc, which is equals to mp into l plus b divided by ab. Okay, so 1 a 2b, so in the sense b into or b plus b plus a. So 1a plus b is our length of the member, so l plus b divided by ab, like this we are getting. Okay, got it. So this is a simplification. Okay, 2b in the sense b plus b. Okay, so that is l plus a plus b is the length of the member plus b. Yeah, okay, so l plus b divided by ab. So that is a this is the solution by using kinematic method for cantilever, or sorry, propped cantilever subjected to point load in the varying distances. So thank you.